Hey, Jono, you back? Bit unexpected for a 9 light year trip. How was it?
Pretty boring, eh, Kev? The lead up was definitely more interesting than the main event. The whole to and from Alpha Centauri thing was barely long enough to binge watch all the lectures in the course in the end.
Really? How's that work?
Well, it's a bit of a long story, actually. The dude who runs the course, well, his mates was some guy named Fox, whose mates was some guy named Ringo, who recently moved to Newtown, eh? Anyway, Ringo was telling us about this TARDIS that's supposedly hidden on a tiny island in Lake Burragram. You know, that huge lake in the Blue Mountains where all of Sydney's water comes from.
Like the time machine from Doctor Who?
Yeah, exactly, like Doctor Who. I didn't believe it at first, but we hiked for 5 days in, and sure enough, there it was. Before the hike, some Dogecoins changed hands on Silk Road to get us some totes special mineral called Cyton 7 or something. Anyway, after Adam put an imprint in the Bryode nebulizer and gave the control panel some percussive maintenance, I was good to go.
But wait, the rocket thing. Weren't you in that SpaceX launch?
Yeah, we staged the whole rocket thing, eh? We slung Elon some spare Doge to just add some extra footage to the Starlink launch for us. It was part of why it was the craziest physics demo in human history. Struth, 9 years in a tin can financed on a university budget? Yeah, I'd call that Falcon heavy too, mate, if you know what I mean.
Yeah, true. So back in time for footy season after all.
Yeah, and exams. I reckon I'm on for a 99 HD, given I now have access to a TARDIS whenever I need one. It's like Jatana, we're on the home stretch. The hardest part of my half of the course is now behind us in the last lecture, where we had to make a big conceptual jump from systems where you have a small number of observable outcomes, like spin up and spin down, where you can use a vector-based approach, to systems where you essentially have an infinite number of observable outcomes, for example, a whole pile of positions along a continuous line, and you evolve towards a function-based approach. Where I want to go this week is to pick up the uncertainty principle, and I'm going to do that in 3 parts across the 3 lectures. In today's lecture, what I'm going to do is look at the idea of measuring more than one quantity at once, because ultimately that's at the heart of the uncertainty principle. In the second lecture, what we'll do is look a little bit more at what uncertainty means from a statistical standpoint, just to set ourselves up for what the uncertainty principle actually is. And then in the third lecture, we'll get that uncertainty principle and finish my half of the course. So let's get some slide up. Where I want to start today is with the idea of measuring more than one observable quantity at once, okay? For a quantum spin, you could imagine that possibly being wanting to measure the z component of the angular momentum at the same time as the x component of the angular momentum. And as you remember way back in the course, that's not something you can easily do because the measurement changes the state of the system in that particular instance, okay? The other thing that system where you might have the same problem is the particle traveling along a line, right? It's got some position x, it's got some momentum p, and in an ideal world, to properly characterize the behavior of that system, you would like to know the momentum and position at the same time. And again, that's something that ultimately the uncertainty principle says we can't do. But in order to get to that uncertainty principle, we have to think about what it is in our mathematical framework that governs our ability to measure multiple observable things at the same time. Okay, so let's start from the position that we already know from our discussion of operators earlier, which is that every observable is connected to an operator. And we can have some generic operator that we call L that's an observable measurement of a system, okay? And so what we know is that a measurement of L leaves the system in an eigenstate corresponding to a single eigenvector of L that corresponds to whatever the eigenvalue was that was measured. So if we think back to our spin, it may be in some arbitrary superposition. We'll do a measurement of the angular momentum component along Z, and if we get a +1, that means it must be in the upstate, and that measurement leaves that in the upstate. Okay, so what we're going to do is imagine a hypothetical system here. We're not going to attach real measurements to it for the moment because most of the real measurements we can think to do cannot be done simultaneously. There are measurements in quantum mechanics that can be done simultaneously. We just haven't seen examples of them yet. So what I'm going to do is sort of abstract this up to thinking about two possible measurements we could do, right? They would be two different measurements on the system. To give you an example, it could be sigma z, sigma x, it could be x and p. And they're going to have respective operators L, and we need a second one, so we will call it M, okay? And what we're going to do is we're going to start with the assumption that actually in this situation, what we can do is measure both of those things simultaneously for a given state without one of the measurements wrecking the state of the system for the other. Okay, so we're enabling simultaneous measurements. What that ultimately means is that the eigenstate that the system is left in after the measurement of L and M must simultaneously be an eigenvector of those two operators. Okay. In other words, what we're basically arguing is that if we have a system A, we can measure L and we can measure M. Neither of them affects the other, and the final state that we end up in must simultaneously be an eigenstate of both L and M. Okay, and we're just going to allow this as a hypothesis and see where that points us to in terms of a mathematical requirement in our framework, so we can build from there to understand a little bit more. Let's get some writing up. So what we're going to do is we're going to assume that we have state vectors in this system, and we're going to write them in a very slightly funny way. We're going to write them in a way that looks like this: lambda I, comma, mu a as a ket, where we have a system that's one thing here. So this could be one spin, it could be one particle. This is not a notation like you would have in entangled spins where you've actually got two spins, right? This is one system. What we're basically saying here is that if I apply the operator L to this particular state of the system, lambda I, comma, mu a, it will give us a eigenvalue lambda I and return that state as the eigenvector or eigenstate. Okay, so that's the first part. If we do a measurement of M instead, the operator M acting on this state, lambda I mu a, will give us the eigenvalue mu a and the state lambda I mu a. And so what we're really saying here is that this state, and we could call it A if we wanted to, we could call it psi, it's a single state for a single system. All we're saying here is that if L acts on it, the eigenvalue lambda I pops out, and if M acts on it, the eigenvalue mu a pops out. Okay, we could, if we wanted to simplify this, write it as just lambda comma mu. But usually what happens is in a system, some measurement will get you not just one eigenvalue, but a whole pile of possible eigenvalues, right? Quantum spin has two possible eigenvalues. If we look at position, we've essentially got an infinite number of eigenvalues, and we want to be able to track that in some way. So that's why you've got the little tail factors as subscript there, the I and the A, so that for all the possible eigenvalues lambda, we can keep track of which one it is, and of all the possible eigenvalues mu, we can keep track of which one that is. Okay, and so the comma only exists to tell us that there's two possible outcomes depending which of the measurement you do, and that this state is an eigenstate of both of those possible measurements. Okay, once you get that idea, the rest of the math that follows here is actually pretty simple. So what we're going to do, and you will understand this idea from lecture 8 where we dealt with entanglement, is we're going to do two measurements simultaneously on this system. And we're going to do that by basically applying the two operators sequentially to the state. Okay, so if you remember back to lecture 8, what we had was some entangled state. We had a spin operator for Bob, a spin operator for Alice, and we could just apply the two operators to find out what the state was after the measurement. So if we're going to do this, we're going to measure Lm and apply it to this state lambda I mu A. Okay, and some of you will go, well, hang on, why are you doing the measurement M first before L? Part of the argument here is actually in a second to reverse those two operators and do L first and then M, and then look at what's different about the two. Okay, so we're just going to consider simultaneous measurements here, where we do that measurement just by acting once very slightly before the other, and then repeat the same measurement where the other one comes just before the second one, so that we can kind of converge on actual simultaneous measurement here. So if we do this, what we're going to get is the operator L acting on, the closest operator to the ket will act first, right? So we'll have M acting on that ket, and so this would be mu A lambda I mu A, like so. Okay, so all we've really done is just act the operator M just as we had in this equation up here. Now the operator L can act on that state, and of course mu A is just a number because it's an eigenvalue, and we can take it out the front. So we can write this thing as mu A L acting on the ket lambda I mu A. And of course, now if L acts on that ket, we will get lambda I popping out. So this would be mu A lambda I mu A. Okay, fairly simple little piece of logic there. Now what we'll do is we'll reverse the order of those two measurements, right? So let's imagine that L acts on the state before M. And so what we would have is ML lambda I mu A is equal to, so the M will stand out the side while L acts. So we'll have M. L acting on that state will give us lambda I mu A, like so. And then of course, same idea, lambda I is a number, so it can pop over to the other side of the operator, and so what we've got here is lambda I M lambda I mu A. And then now the operator M will act on that state, and it will get us a mu A. So what we'd have here is lambda I mu A lambda I comma mu A, like so. Okay. All right, now there's one last little step we can make in here, which is that we know that lambda I is just eigenvalue, so it's a number, and mu A also is an eigenvalue, so it is also a number, and numbers commute. So, you know, the product of two numbers is the same whether they're this order around or that order around. So this second expression here, what we can do if we want is just reverse the order of the numbers, and they will be exactly the same thing, right? Like so. Okay, so what this says in here is that this term here is equal to this term here. And what it means working backwards is that we can say that Lm on the state lambda I mu A will be equal to ML acting on the state lambda I mu A. Okay? We can subtract one of them from both sides to get an expression that looks like this. Lm lambda I mu A minus ML lambda I mu A is equal to 0. And then we can cluster our terms together on the operators. So we can basically factor out the state. So what we would write here is Lm minus ML lambda I mu A is equal to 0. Okay? We're back in another one of these places that we get to multiple times in this course and multiple times in physics, where the product of two things is equal to 0. And what that means is that one of those two things must be 0. Okay? One possibility is that lambda I mu A is equal to 0. And if that's true, what that means is that that eigenstate just doesn't exist, right? So if we're in this situation, we also have Lm minus Ml equals anything. And so what we're saying here is that if this holds, we don't have a state that's simultaneously eigenvector of both operators L and M. Okay, so that's option 1. Option 2 is that our state lambda I mu A here is not equal to 0. In other words, we do have a simultaneous eigenvector of our two operators L and M. And in order for equation 1 up here to hold, we then require that Lm minus Ml is equal to 0. Okay? Now, one easy way to think about this is actually to undo the our move earlier to bring all of the operators to one side. So what we can do here is write this as Lm equals Ml. In other words, what we're saying is that the two operators L and M commute, right? So Lm is the same thing as M times L. This thing that we have up here is a thing in quantum mechanics that we call a commutator, and we usually write it with square brackets like this. Square bracket L comma M is equal to Lm minus Ml. And so if our commutator Lm is equal to 0, then L and M commute, and L and M are simultaneously observable. So let's just recap quickly here. What we did was we started with from a hypothesis of having two things that we want to measure with operators connected to them L and M, and the existence of a state that is simultaneously an eigenstate of both L and M. And what we arrive at is a mathematical requirement regarding those operators, which is that those two operators must commute in order for them to be simultaneously observable, okay? And we write that commutation relation as a thing that we call a commutator with square brackets around it. The best way to see this is basically from the context of one does not simply reverse the operators in quantum mechanics, okay? In a lot of situations, that commutator is not 0. The fact that that commutator is not 0 tells you that the one order of the commutators is not equal to the opposite order of the commutators, and so you need to be very careful in quantum mechanics about simply switching the order of your two operators. Okay, sort of ties back into what we were talking about in the first lecture in terms of logic in quantum mechanical systems. I think I'm going to stop there for the first half, and what we'll do in the second half is start to look at what actual commutators look like, right? Because now that we know that ability to do simultaneous observation is connected to commutators, we're going to want to understand a little bit about the mathematical properties of commutators. And so what we'll do is look at one very interesting property, and we'll also show that if you make the commutator that corresponds to position and momentum, you get a commutator that is not equal to 0, which starts to tell you something about your ability to measure P and X simultaneously, that ultimately, as you see, as the week goes on, will be connected to where our uncertainty principle comes from.